Welcome. In our last lecture, we spoke about the Bloch theorem. It was a very technical session in the sense that it was completely mathematical. Bloch theorem is really a mathematical theorem. And what we did is we proved it, and from there we obtained a few things that are interesting about solid state systems. So basically systems in which the atoms or the molecules are arranged in a periodic three-dimensional array. Okay, today we want to talk a little bit more around that and elaborate around that and try to create an intuition of what the Bloch theorem means and the results that come out from it, and essentially build, at least intuitively, the notion of what, when formally done, is called the band theory of solids. Okay, so essentially, what we found, or we arrived in the Bloch theorem, was that the solution of a Schrödinger equation that we can write here, which is minus h bar squared over 2m Laplacian plus u of r on the wave function is equal to the energy, which we denoted by a curly e, psi. And the most important part here is that we assume that this u is periodic in space. So that is a function. We don't know the exact shape of the function, but we know it repeats over space, in the entire space over a certain period, and we assume that there's a period for all three dimensions. So from there, what we obtained is that the wave function has to be of this form. So psi sub n k of r will be equal to e to the I k dot r times u sub n k of r. Okay, and what we said is from the demonstration of the Bloch's theorem, this u sub nk function, it has to be a function that shows the same periodicity that the potential shows. So it doesn't have to have the same shape, so the exact same values, but it has to have the same periodicity. So if let's say u capital U, the potential, repeats over, let's say, 1 nanometer, then the small u, this other function down here, will also have to repeat over a period of 1 nanometer or so. Okay, and so this wave function now has two parts. These periodic function, which I would say, and let's say for the sake of this argument, is boring. It's a function that has the periodicity of the potential, which is the same periodicity of the crystal. So it has the same periodicity of the arrangement of atoms or molecules in the crystal, but it's basically a function that is there more or less in the background. It's not interesting, and so on. But we have this other part, the e to the ik dot r. And this basically is a plane wave with a k vector in the direction, well, given by this k, which, if you remember, k comes up as a label, or comes out of constructing what we call the reciprocal lattice, and not just the reciprocal lattice. It can only acquire certain values within what we call the first previos zone. So I'll just make a little drawing. So we had to introduce something that we call the reciprocal space and the reciprocal lattice. So the geometrical arrangement of atoms produces another abstract periodical arrangement of points in a different space, which we call the reciprocal space or the K space. And this abstract space has a lattice that is related to the original lattice as well. We discussed that in the previous lecture. But the interesting part is that in the process of demonstrating Bloch's theorem, if we took the unit cell in this, which I draw here just two-dimensionally, but it's actually a three-dimensional piece of this reciprocal space. The unit cell that has points, for example, there in the corners, if we assume it's a cubical lattice in the reciprocal space, was divided into many little subdivisions. And these subdivisions created a new finite grid, so it only has a finite number of points, which are a very superfine division of this unit cell of the reciprocal space. This unit cell of the reciprocal space, we called it the first Brillouin zone. And it so happens that this K vector here, that comes out naturally from solving or demonstrating the Bloch's theorem, can only acquire a finite number of values, which are all these bunch of intersections here, which form a really very fine grid with many points of the order of the number of atoms in the crystal. So we're talking about Avogadro's number, or 10 to the 23 or so. Atoms in, not atoms, possible values of K. So for every value of n, which we said is a discrete infinite number of states, there will be a number that is the same as the number of atoms in the crystal that can be acquired in this reciprocal space. Again, this sounds very abstract and confusing, but this first Brillouin zone is just a chunk of space in this reciprocal space, which we had to divide in a very fine yet finite number of possible values that the K vector can acquire. And these are the only values that the K vector can take for psi to be a solution of the Schrödinger equation in the case of the periodic potential. Okay, so all of this again is very abstract, is very technical, and what we will try to do today is to make sense out of this. Okay, so the first thing I want to introduce is the notion that this e to the I k dot r function, and then we have the other part, the unk of r. I want to introduce the notion that this plane wave, really, at least intuitively, that's the one that represents the electron moving along the lattice. Okay. Second, this K vector would, in principle, if we're thinking of not a particle but a wave, which the electron is in a sense, this K vector would represent exactly that, the vector that defines the direction in which the wave propagates, and the magnitude will represent basically what will be related to its wavelength, and in terms of the de Broglie wavelength, it would also be related to the momentum. Again, we had a formal discussion last time why this K cannot be the momentum, and it has to do with the fact that K is one of the labels that come out from solving the Schrödinger problem, and this means that we need to know K in order to know the energy. But if we know the energy, we cannot know the momentum, and therefore K cannot be related to the momentum. However, intuitively, we still understand K as if it was the momentum, and in the sense that the momentum, or what we call the lattice momentum, is going to be exactly h bar k. Okay, so we define this new number, which is formally not the momentum of the electron, but that intuitively we think of it as if it was the momentum of this electron moving along the lattice, moving through the crystal. So this relationship between the actual momentum of the electron and the lattice momentum cannot be established. They are not the same quantity, but again, intuitively they are the same. And there is this relationship that we will now try to introduce between the two quantities. So this intuitive momentum or lattice momentum and the energy that each one of the k vectors labels or represents in the solution of the Schrödinger equation. So first I want to take a step back just for a second and forget about the Bloch's theorem for just a minute in order to try to build a little bit of intuition. If you solve the problem of the infinite potential, this has been already discussed. What you obtain is a series of so if this is if this is the potential, it can be infinite or finite. It doesn't matter. If you have a potential a square well, what you obtain is a series of energy states which are spaced with higher and higher spacing for each one of them, and we label them. We call them n equals 1, for example, n equals 1, n equals 2, and so on and so forth. Okay? If now, and this is part of your homework now, we solve a slightly different potential. Let's assume that you have a finite potential, a finite square well, and we introduce an intermediate barrier here. Okay? And let's assume, just for a second, I will draw them in blue. Let's assume that these ones were the levels of the original well. So the well that runs from here to here without this intermediate barrier. What happens if you solve now this slightly more complicated potential with a barrier in between? Well, what you will get is that essentially the energy levels that fall within or below this barrier. So, for example, these two here. This one that falls down here will actually be split into two. One that is slightly higher and one that is slightly lower than the original, which I will draw again in blue, than the original level. So the solutions of these problem with a barrier in between is more or less the same solution, but each one of the solutions is now split into two solutions that are just very slightly shifted away. And if what you do is, instead of putting just two wells, you put many wells, what will happen is that all these solutions will actually be split in many levels. So let's assume that you have now something with a big number of wells, a big number of barriers in between. If you assume that now again the original level was somewhere around here, what you will get now is a collection. These level will now have split into many levels that are all more or less packed together. And I invite you again, as part of the homework, to do this exercise. Maybe just do two, and the case of two here and three. But the thing is, there will be a collection with many levels that pack around this original level that you had in the original well. And what we obtain is that this single level now has converted into a very, very densely packed, depending on the number of levels, of course, or of wells, sorry, a very densely packed band of many, many, many levels, all almost overlapping each other. And if you do this not just with square wells is relatively easy to do, but if you do it now with atoms, what will happen is basically the same. If you have now a bunch of nuclei and electrons and so on, what this will produce is a potential that looks like this. We've already discussed that in the previous session, so it's periodic potential, but regardless of the periodicity of the potential and so on, what we will obtain is that if the original energy levels of a single individual isolated atom was, let's say, this, the solution for this periodic arrangement of atoms will now be converted into a bunch of densely packed levels that more or less arise around the original level. That's more or less the concept. So essentially what happens is that the single level, as you add atoms and you make this a periodic, more complicated system with many atoms, will split into many levels that form what we call, so this original level n equals 1, for example, will become a densely packed bunch of levels that we still label with 1, but we still have, all of these levels are different. They are represented by different wave functions, and they will have different energy values. So we need to have additional labels to be able to distinguish all these different levels. And those levels are exactly what we call the K vector. This K vector, which has 3 labels, K X, K Y, and K Z, will be we have, each one of them can acquire only a finite number of values, as we already said, and it's related to the number of atoms. So if we bring together a big number of atoms, the number of possible values that these can acquire will be much higher, and of course this is related to the number of levels that will be generated in this bunch over here. So this bunch, as I said, is what we call a band. So is an energy band, and depending on how things happen and details that we will not discuss here, the original levels of the atom, for example, or of the molecule, when arranged in this periodic three-dimensional array, we essentially produce these bands of energies that sometimes they will be separated. So n equals 1 and maybe n equals 2 will be separated. So what you will end up with is a bunch of levels over here and a bunch of levels over here, which are n equals 1 and n equals 2. I think I'm in the middle of the screen right now, so I will just remove myself. Okay, great. So essentially what you obtain is this initial bunch of or this band of energies that is related to the first level of the atom or the molecule, and this bunch of levels or this band of levels that is related to n equals 2, and the same applies to n equals 3, 4, 5, 6, 7, 8, 9, 10, and all the levels of the molecule will split in this really large number of levels, which is basically the same number of atoms in the crystal. Okay, so and the difference between all of these ones will be that each one of them, let's say, for example, let's say this first level right here, this one will have one combination kx1 kx2 comma kx sorry k x y and z k y k z, sorry, 1 and 1, and let's say another level somewhere around here, a second level around there, will have kx2 ky2 kz2 and so on and so forth. So each one of these different levels will have a different combination of kx, ky, and kz. So we are able to distinguish between all of these levels that pile up and that form this very densely packed band of energies. And again, two things can happen. One is that there is a space, like in this case that I drew here. So there is a space here in between the two bands, or the other case is that bands could overlap and some of the levels of one of the bands and the levels of the other more or less overlap each other, and then we don't have what we call a band gap. Okay, we will go into all these details in just a second. Okay, so now that we have the notion that these bands should arise, I want to make a very interesting note. If you realize these crystals, let's take just a crystal. It could be a piece of salt, the salt, for example, sodium chloride that you use to prepare your meals, or it could be quartz or gallium arsenide or silicon. It doesn't matter. These crystals are in themselves macroscopic quantum systems. So the levels and all the quantum properties of propagation of electrons, which in the end define the electrical and optical properties, and also the mechanical properties and so on, are actually defined by the entire crystal. So it's no longer, I mean, quantum systems, we used to think of quantum systems as very small things, atoms or molecules, individual atoms or molecules. But in this case, the quantum system is something macroscopic. You can have a grain of salt. It can be much more than a grain. It could be a big chunk of salt. You can find these kinds of things in mines. There are single crystals, or you can grow them in laboratories, and you can have these macroscopic quantum systems which have defined properties that are related to the entire extent of the crystal. The number of levels, the labeling of the levels, and so on, is determined by the entire set of atoms. It's not just one atom. Is the electronic properties and the levels and so on are defined by the entire potential, defined by the entire crystalline structure. And that's something that is very, very interesting and very different to the previous quantum systems that we have discussed. So solid state materials are themselves macroscopic quantum systems. Okay, great. So now we said each one of the energy levels. I will draw again here a band. So let's assume that we have a band. It could be n equals 1 or n equals 2 or n equals 3 or whichever. It doesn't really matter too much. I will just draw one band and draw here maybe another one. I'll just focus on one right now. So let me erase this bit here. So the question now is, what is, I mean, we've already said that distinguishing between this level here and this level here and other levels, let's say here, is about finding the correct, so this is K1, this is K2, for example, this is K3, and this is K4, and the difference between all these levels is going to be the combination of these three coordinates of the K vector. But not only that, also the energy. So now the question is, how do the energy and the K vector relate? Okay, and this is when we start coming back to the Bloch's theorem. So the question is, what is the relationship between the energy and this K vector? And again, just building up on these abstract, on this intuitive notion that K and the momentum, well, with an h bar in between, are the same, or that this K vector really represents the wave, it does represent this wave vector of this plane wave, and that the plane wave is the electron just moving in the lattice. What we would expect to first approximation is that if the momentum, let's say, or this lattice momentum is proportional to K, sorry. And classically, what we have a relationship between the energy and the momentum. So so the energy of a particle is going to be p squared over 2m. So from these two expressions, and again, this is strictly speaking incorrect, but it's just, I just want to create some sort of intuition around this. So if we combine these two and we assume that the momentum that is in the two equations is the same, which we know it's not, what we obtain is that the energy as function of the K vector, and let me just put it here as a number. Let's think one-dimensionally first, just for the simplicity of the argument. What we will have is that the energy is going to be h bar squared times K squared divided by 2m. Okay, and this implies that the relationship between the energy here and the K vector here is basically a quadratic one. So I'll just draw that here for the moment. So let's put here the K vector here. I'll just put it as a number, and the energy here. And what we will obtain is that this should be a quadratic expression, basically a parabola. And this is then the way the K vector and the energy relate. So K vectors that are very close to zero here basically have very low energies, and as you move to higher K values, in principle the energy of the band increases and increases quadratically. So this means that these levels here and the level here and the level here, each one will have a bigger and a bigger K for that matter. Again, K is a vector. We're thinking at the moment just in a one-dimensional thing, but in principle K is not just a one-dimensional line, but a two-dimensional or a three-dimensional, or lives in a three-dimensional space. So for each combination of Kx, Ky, and Kz, the energy will be the square of Kx plus the square of Kb plus the Ky plus the square of Kz. So again, it's not worth trying to draw it because it's impossible. But the idea is this one. So this is essentially what we call a parabolic band. Again, this is not entirely true, but at first glance it gives us an idea of how to relate the K vector of each one of the levels over here. So each one of these levels will have a K and an energy that has a relationship with each other. Let's be very careful, although here I painted the curve as if it was K was a continuous variable, we know that K can only acquire a finite number of values, and they are all within what we call the first previous zone. So in that sense, First of all, K cannot acquire any values. It will be limited to having values between certain boundaries, which are the boundaries of what we call the first Brillouin zone. Again, we can do the argument three-dimensionally, but it just makes things a bit more complicated. And the other thing is it cannot acquire any values here in between these two. The values that the K vector can acquire are just a discrete set, which I will just paint here in green. So it's, although it is a very big number, so it's a very densely packed number of equidistant points in the K space in all three dimensions. Here again, I should do it in one dimension. It can only acquire those values, and then again, the energy can only acquire this finite number of levels or values as well, right? Then again, of course, there are many here missing. But if you look at these values of the energy, essentially this is the densely packed band. So these are exactly these values that we see here. So all these values that the energy can acquire are exactly these values that form around the, let's say, original value of the energy level of a single atom or a single molecule or something like that. So this band is defined by these values here. So again, I'm just trying to create an intuition, although I'm saying things a bit loosely and not in a very formal way, and some of the things that I'm saying are strictly not entirely true, but intuitively that's the way we understand them. Everyone doing solid state physics understand them this way, intuitively. So that being said, one of the interesting things is, okay, since we have a very densely packed, although finite, number of points, for every practical purpose, we will think of all these points in the K space as if it was a continuum. So in principle, they are so close to each other and everything is so densely packed that we can think of it as if it was a continuous thing and just think in continuous terms for the rest of the arguments. Although formally, we have to bear in mind that only these discrete number of values are allowed. Not just discrete, but actually finite number of values are allowed. So one other very interesting aspect of this quadratic relationship that we have shown here is that let's for a second differentiate this expression here we have for the energy. So this expression, let's differentiate it with respect to K. What we obtain is the first derivative will be the first derivative of E with respect to K is going to be h bar K divided by M, and the second derivative of the energy divided with respect to K will be basically h bar divided by M. Okay, so h bar is a universal constant, so we will not discuss that. The main interesting thing is that the second derivative of the energy with respect to K, it's actually the inverse of the mass and h bar there, but let's not worry about that for a second. So what this means is that the curvature of these, if we look into this quadratic relationship, so this parabola, a parabola. So the second derivative of a parabola, what does it measure? Geometrically, when we have a very flat parabola, it means that the second derivative will be very low. So this means, and when we have a very curvy, very sharp parabola, what we get is a very high value of the second derivative. So interestingly, the curvature of the parabola tells us about the mass of the electron. So now is when some of these differences between the momentum and the momentum in the crystal start arising. So this lattice momentum. This m, this mass that is related to the curvature of this parabola. So the exact relationship between the k vector or the k value and the energy will define the effective mass of the electron in the lattice. And this is a very important concept. So what we have, if we move on to a new page that we have a little bit more space, is we have, we have this relationship between the k vector and the energy, which is a parabola, and this parabola is basically the second derivative of this, so the second derivative of the energy with respect to k will be h bar divided by m, and here this m, I'll make a small distinction. This m is not the mass of the electron in free space, it's not the mass of electron that you can go and check in any physics book. It's what we call the effective mass. So we put an m star there. So this mass here is actually not again, it's not the mass of the electron in free space, is what we call the effective mass. And let's think of once again of the meaning of this plane wave that more or less introduces the k vector into the solution to the Schrödinger equation due to the Bloch's theorem. This sounds very complicated, okay? So what you have is a wave that is moving in this periodic potential. And this wave is basically a plane wave with another component there that is a background with that doesn't really matter. So we have this plane wave, which we think and we intuitively understand as the electron propagating, as an electron moving through the crystal. And this electron will have an effective mass that is related to this particular relationship between the k vector and the energy. And again, this has all been done with very simplistic arguments. The truth is that the structure of a band, of a real band in a real crystal, is not necessarily just a very simple parabola. It can be something a bit more complicated. So it could be something that is like that. This is actually the shape of several band structures of real crystals. For example, gallium arsenide has a band structure that looks a little bit like that. The interesting part is that this is the relationship between the k vector, which we already said is related to the lattice momentum, and which is something very closely related, at least intuitively, to the momentum of this electron propagating through the lattice, and the energy. And we said that when we have the case that the band structure is not a perfect parabola like we have drawn here, but something a bit more complicated as what we have up here, is that each one, then the second derivative is no longer constant. That's the first point. So the only curve for which the second derivative is constant for all k values is the parabola. When the curve deviates from a parabola, then each point will have a different value of the curvature. So the curvature here, I'll just change color. So the curvature here, and the curvature here, and the curvature here, and the curvature here, and in each one of these points is going to be different. So this means that the effective mass of each one of the electrons, or not of each one of the electrons, depending on the particular quantum state occupied by the electron in a real crystal, it will have a different effective mass value. So each one of the electrons will have its own value for the mass. That starts complicating things. However, what we have in real crystals, in real band structures like the one up here, is that electrons tend to feel the states close to what we call the values, which are the minima of this curve. And close to a minimum, we can always do the approximation of a parabola. So close to a minimum here, well, this one doesn't look very nice, but close to a minimum, we can always approximate any curve reasonably well by a parabola. So if we use a parabola here, it approximates reasonably well the curve near any minimum. So here in the vicinity of a minimum, we always have, although the actual band structure could be something that is not necessarily a perfect parabola or something very simple, we can always approximate at least close to the values, to the minimum of each one of the minima of these band structure. We can always take parabolas and approximate at least locally the band structure as different parabolas for different values. And this is what we call the parabolic band structure. So in principle, we can always assume that the electrons will be, at least when they are close to thermal equilibrium, will be close to the minimum of the valley, and also that they will be using, even if they are not in the actual global minimum, but in side valleys, they will tend to feel the states that are close to minima first, and within the vicinity of these minima, we can always approximate the curvatures as constant, and we can always approximate the mass as constant. And therefore, if you go to solid state books, what you can find, or solid state tables, what you can find is the values of the effective masses for different semiconductors, or for different materials, metals, or other crystals. You can find what the effective mass values are for different points in the band structure, which are typically minima. And people tend to give them names. For example, this minimum that is close here to zero, the point where of k equals 0 is what we call gamma. So k equals 0 or gamma are synonyms. They mean exactly the same. So when we say the gamma point, we are referring to the point of 0k vector. So the origin in this reciprocal space. And some others, for example, for gallium arsenide, there's what's called the X valley and the L valley, and so on. It doesn't really matter, the labels, they have many names, M and so on. It doesn't really matter. I don't want to go into all the details of how to name all these high symmetry points in the first brio and so on. It doesn't really matter too much, not for the purposes of these curves. Of course, if you want to do band structure calculations, or if you want to use these values, it's worth that you go to books and understand a little bit better what each one of these labels mean. But for the sake of these arguments, we will always assume here that the bands are just very simple parabolas, or in the worst case scenario, a structure like this one that can be approximated locally by parabolas. And again, this is what we call the parabolic band structure, or the parabolic approximation to the band structure. Although the band structure is really this more complicated curve that I drew up here in yellow. So let's now assume that we have a completely empty crystal. So we only have, I'll draw it here, and again, it's just I'll just put a square lattice in 2 dimensions for simplicity, but it could be any lattice. Okay, so let's assume now that we have, now again, just a finite lattice, so it's a real crystal with 10 to the 23 atoms or so. So it's a very big number of atoms, but it's finite number. And let's assume that we only have the nuclei arranged in the correct three-dimensional arrangement, and we start putting electrons one by one in order to balance the charges. One of the things that we assumed in the Bloch's theorem is when we built it is that electrons didn't interact with each other. So here let's be careful with these little details, but let's assume for the moment that we start putting electrons in there and that the electrons don't interact with each other. They only see the potential from the lattice. Okay, interactions that arise from electron-electron interaction. So the effects of these in terms of the properties of materials is something that we will not cover, but we'll just briefly mention maybe at the end of this lecture. But at the moment, let's just think in terms of, okay, you have all the nuclei there already arranged in the correct order, and let's now start putting all the electrons that are needed. So you will, if these were hydrogen atoms, you would need only one electron per nuclei. Of course, hydrogen doesn't produce crystals, but let's think of other materials. If it was lithium or for example, you would need 3 electrons for each nucleus, and so on and so forth. It doesn't really matter. The thing is, we start putting electrons and electrons and electrons, and what happens is typically the first few electrons will start going to the lowest possible levels. So I will draw over here let's say this is the first band, and then then you have the second band, and then you have the third band, and so on and so forth. It doesn't really matter too much, okay? And we start putting electrons, and when we put the first electron in the lattice, what it will see is not just the potential of its or one of the atoms. What it will see is the potential of the entire lattice. So the levels that correspond are the levels of the lattice, which are these ones that I drew there. So this band structure, or these bands that I've put there. So if we put the first electron, it will try to go to the lowest energy possible. So it will populate this very first level. And then I put the second electron, and it will try to use the next available level. So let's say this one. And then we put the next level, and it will try to use the next available level, and so on and so forth. And we start filling these levels until we have put enough electrons to balance charges out. And this will bring us to 2 possible scenarios. Let's say we have completely filled this band, and there are here 2 possibilities. I will draw another band structure that looks similar over here. So there are 2 possibilities. When we put the last electron that finally balances out all the positive charges of the lattice, what we can have is that all these levels here are filled, for example, and all these levels here are also filled, and exactly when we put the last electron, we completely fill one band, okay? And then I'm out of electrons, so there's nothing else I can put in there. Or there's one other possibility. I start filling all these electrons, I start filling. When I finish one band, I start with the next lowest energy level, and so on and so forth. But let's say at some point I run out of electrons when I'm still in the middle of the band. So this is the only 2 possibilities. So either one band is completely full, or one band is half full. There are no other possibilities. And this very thing has very, very deep effects on the properties, but particularly the electrical, but also the optical properties of the material. Because when we have a completely full band and then the next band is completely empty, what we have is an insulator. or a dielectric material. And when the band is half full, when the last populated band is full, what we have is a conductor or a metal. Okay, and basically what happens here is that let's think again in terms let's just focus on this band here, whether it's the insulator case or the conductor case. So what we will have is I will draw here the band structure. So let's assume it's parabolic as we have discussed here, and one possibility is that let's put here the boundaries of the previous zone. So one possibility is that it's half full. So this means that all these states over here will be full, and then all these other states over here are empty. Okay, so this is this case. So you have the empty levels over here, and the full levels in the lower part of the band. And this means that all these electrons over here, in the states that are full and the electrons that are there, can acquire additional kinetic energy. So essentially, we can accelerate them and promote them to levels that are up here that are still free. So we can make all of these electrons acquire more kinetic energy, more momentum, or more lattice momentum if we are very formal, and accelerate them. And this is actually producing a current. So if we can accelerate them and give them more momentum, this means that the wave will travel with a different k vector, and we can more or less point all these k vectors in the same direction and so on, and produce an actual current. This is what happens in a conductor. When we have, so this means that, again, these electrons over here can jump to higher energy and also higher k vector states, and therefore we can produce an electrical current. While in this other case, the insulator case, which I will draw over here, what we have is that, let's say this is the first previous zone, this is the k vector, which I forgot to put in the previous, this is the energy, this is the energy, okay? And if all these, all of these states are occupied, just like we have over here, in order to be accelerated, what we would have to do is to occupy a level with a not just slightly higher, but much higher energy. So instead of just being able to slowly and softly accelerate the electrons, we would have to give them a very strong kick to promote them to a different band. Okay? And that can be done, for example, by optical means, so by photoexcitation, if we have photons of enough energy, but this cannot be done just by applying some electric field and slowly accelerating the electrons. And therefore, all these electrons that are over here cannot be promoted because to energy states that are slightly higher in energy and slightly higher in momentum, just because all the states are occupied, all the states in the band. And therefore, we cannot produce an electrical current in these kinds of materials. And that is what makes the difference between a conductor and an insulator. Okay? And here I want to take the opportunity to introduce a couple of other names that we use for these things in solid state physics. So in this case, let's say here we have the energy state, basically the energy that separates the highest occupied level and the lowest unoccupied level. Okay, so this energy, the energy that corresponds to this level, is what we will call the Fermi energy. Okay, and so the Fermi energy is basically the energy that separates the highest occupied level from the lowest unoccupied level in a solid state system. And the Fermi energy can be within a band, or it can be in between two bands. So the Fermi energy could be here, and and depending on this is then the material will be either a conductor or an insulator. Okay, great. In addition to the Fermi energy, we have one other concept. If we go to the K space, for example, we can define now these edges of the occupied area within the Brillouin zone. Okay, within the first Brillouin zone. And these limits of the first Brillouin zone that also separate the occupied and the unoccupied K states are what we will call the Fermi surface. Of course, when we draw these in 3 dimensions, K, remember, K is a 3-dimensional vector, which here we are just drawing as a 1-dimensional variable, but it's actually a 3-dimensional thing. So this means that in I will try to do a 2-dimensional drawing. So let's assume that here we have the first Brillouin zone, so 2-dimensionally. So we have there is the collection of all possible K vectors allowed by the solution of the Heisenberg problem. So these are all the possible values of K that the wave function can acquire. And within this, if we assume that this is parabolic, or that we have a parabolic band, this means that now the Brillouin zone, let's assume, is okay. At the moment you're seeing it like that, but let's turn it like that. So it's basically a plane thing. It's a plane square in this case. What we would have is then a paraboloid, which will be the parabolic band structure. Okay, and this means that the energy levels will be feeling from the gamma point, which is the point in the center of the first Brillouin zone, or the K equals 0 point, and it will start filling, and we will still put electrons on electrons, and they will all tend, I mean, as long as it's still a parabolic band, they will all pack up in the region around the gamma point. And at some point we will have put all the electrons that we need, and these will produce a zone that separates the populated values of K. Remember, this is a finite number of points, but at the moment there are so many and they are so closely packed that we are thinking them as a continuum. So all these are the possible K values that are populated, and these are, so these ones in white here, sorry, I'll draw them in green here. These ones are the unpopulated but still allowed states of the K vector. So this curve here that I'm putting, that separates the populated from the unpopulated K vectors, is what we call the Fermi surface. Okay, and so it's essentially the same concept as in the energy. The Fermi energy is the energy that separates the populated and unpopulated energy states. In the K space, the Fermi surface is the surface that separates the occupied from the unoccupied K states. Yeah, okay. So you can go to solid state books and check out the really nice shapes that these Fermi surfaces can acquire for different crystallographic groups and for different Parabolic lattices and so on. So depending on the way atoms are arranged three-dimensionally, this produces different shapes for the first brilliant and so on, and it also produces different shapes for the Fermi surface. And when we go to non-parabolic cases, the Fermi surface can really become something rather complicated, and in many cases very, very beautiful. And I do encourage you to see some of those pictures that you can find on Wikipedia or many other web pages or in solid state books. Okay, let's go back for a second to our previous slide. Okay. Here I will introduce now a couple of terms that are of great importance to our the rest of the course, and that is a special name that we give to some of the bands. So it doesn't matter if the bands I'm drawing up here are n equal 2, n equal 3, and n equal 30, or whatever they are. What we will find is that basically there are two special bands, and these are the bands that are close to the Fermi energy. So in the case of insulators, the last field band will be called the valence band, okay? We note them by a VB. And the first completely empty band is what we will call the conduction band, okay? In the case of conductor, what we will call the valence band will be the last completely full band. So in this case, it's going to be this one, the valence band, and the conduction band is the first half full conduction band. Okay, so what we can see from these two schematics is basically the valence band is the last full band, and the conduction band is the first either empty or half full band. And okay, great. So in terms of dividing these two types of materials, what we can say very generally is that insulators are materials that have an empty conduction band, and conductors are materials that have a half full conduction band. However, there is a third type of materials that are of great technological importance, and that is the semiconductors. And semiconductors, I mean, there is no third option here. So either the conduction band is completely full or is half empty. Sorry, is either completely empty or half empty. But there is no third case here. So the Fermi energy is either within a band or is in between bands. That's it. So what is a semiconductor? And many people would try to give you an argument. Oh yeah, it's something in between an insulator and a conductor. And in certain senses, it's true. But in this way of seeing solid state materials, the question arises: what is a semiconductor? And for that matter, semiconductors are materials that are really, I mean, if we are very, very strict, I would say they fall more in the insulator category rather than the conductors. However, by changing either some physical variables, like for example illumination, or for instance the temperature, or several others, one can create excitation. For example, if the distance between the two bands here, in between these two bands, the valence and the conduction band, is small enough, and we apply a temperature that is high enough, whatever that is, we can start promoting electrons thermally from the valence band into the conduction band. And then this insulator will no longer be an insulator, will start conducting electricity. And the conductivity will be proportional to the temperature. So in that sense, some insulator materials that under certain circumstances can become slightly conductors are really what we call a semiconductor. And these materials are very, very important for many reasons. Among others, they can be used as sensors. You can develop thermal sensors or light sensors or sensors of several other physical properties that are reflected onto the conductivity, and therefore we can use voltages or currents to measure indirectly these other physical variables. And that's what makes semiconductors so interesting. Another aspect that makes semiconductors very interesting is the fact that we can make them controllably conductive, even in the absence of high temperatures or illumination or other changes in physical variables. We can make small changes to the composition, to introduce a few impurities or dopants, we call them, in the lattice structure, and from there we can by controlling the number or the amount of these impurities, we can decide what the conductivity is, and even the type of carriers. It doesn't really matter too much at this point, but we can basically tweak the conductivity of these materials by introducing chemical changes in their composition. So this is all very interesting and is very useful and has opened up the possibility of creating many devices that are very important technologically in our everyday life. So we will discuss a little bit more about semiconductors in one of the following sessions. However, I just want to wrap up our session and continue with the aspects of the band structure. So we've already spoken about the band structure, the Fermi surface, and so on. I want to draw your attention to this schematic. This is a schematic taken from Wikimedia. So it's freely available, it's copyright free, or well, it's under some license that you can reuse. There's actually a lot of very interesting, very useful material in that website. But the main thing I want to put here is the fact that this is what we call the first Brillouin zone in the case of a cubic lattice. So cubic lattices, the reciprocal lattice is also cubic, and what we are drawing here, this cube, is actually the three-dimensional first Brillouin zone. So it's in the reciprocal space, and it has the shape of a cube. In the center of the first Brillouin zone, what you see is you find the gamma point. So there you have the gamma point, which is at k equals 0. And then you have a few other points that are denoted there by different letters, for example, M or X or R. And when you go when you go to different textbooks to look, for example, for the band structure of materials, what you will find is a curve that looks more or less like the ones we've drawn so far. So you will have, for example, here the k vector, and you will have here the energy. However, if we want to give the band structure, what we would have to do is to draw a hypersurface of these three-dimensional variables. So it's a function of kx, it's a function of ky, and it's a function of kz. This means that the domain is three-dimensional, and therefore what we would have to draw is an abstract hypersurface that we can, of course, not draw. But instead, what is provided in the books is actually a curve that looks more or less like, as I said, the ones I've already drawn. So you have a curve that has something like these, for example. I don't know, something like that. And there are several letters marked in different points. For example, here you have your gamma, which is always in the point of k equals 0. Then, for example, you can have your m point, and then you can have your x point somewhere here, x point, and you can have, for example, the r point somewhere else. Okay, so what this means is that this band structure that I'm drawing here is actually the values that the energy acquires as you move along these lines that are denoted there on the cube. So basically, moving from gamma to m means going through this line here. Okay, this line over here, and how the energy changes as you move along this direction in the first Brillouin zone. And then you go from m to x, so basically this other part here, from here to here, what you see is how the energy changes as you change the k vector from this point to this point across this line, for example. And then you have, I don't know, this one over here. So you have the trajectory between r and gamma, and then what you're seeing is the way the energy changes as you move along this line. And in many cases, and given the symmetries and all the properties of these lattices and exactly the symmetries that are present, just picking some of these points and some of these particular trajectories is enough to give you a very good idea of what this hypersurface should look like, and giving you all the necessary information by just drawing a few trajectories along these points. So instead of having to draw something that is impossible actually to draw, this hyper surface that would need a four-dimensional space to be drawn, what we do is we just pick some trajectories within the first Brillouin zone that gives us enough information to know what the band structure will be for these materials. And again, the names of all these points and so on, it's not important. The only one I want you to remember is gamma. Gamma is the zero, the origin of the reciprocal space, or the point of k equals 0. And the rest here is just different points on the surface of the first Brillouin zone that have high symmetry, and then basically the curves that we show here are just trajectories along the different paths within or in between all these high symmetry points. Okay, so now I just want to wrap up the session for today. What we've done is we've tried to create some now intuition from the very technical results we got from the previous session. So in the previous session we demonstrated the Bloch's theorem, and from that several things arised. This k vector, for example, and the existence of the first Brillouin zone, and so on and so forth, and the fact that the solution to the Schrödinger equation with a periodic potential has to be basically a plane wave where this k vector comes into play as the k vector, and another part of the function that is just another background function that has the same periodicity of the lattice or of the potential. And from here, essentially, we now built up what the relationship between k and the energy is. So how are all the levels that are labeled by all these this enormous collection of k, x, ky, and kz combinations that are allowed, how they label and how these k's relate to the energy, okay, which is what we call the band structure, which can be parabolic band structure, for example, or so. So we created this notion of a parabola. From there we moved on to the effective mass. So the effective mass has to do with the curvature of this parabola, and in more realistic scenarios in which the band structure is not a perfect parabola but a more complicated curve, what we obtain is that locally for each one of these points we will actually have a different effective mass, which we denoted by m star, which is essentially the reciprocal of the curvature of this of this curve that relates the k vector with the energy. So essentially the mass will now be not a property of the particle itself, but a property of the particle occupying any particular quantum state of these quantum system that we call a crystal. And finally, we discussed the differences between conductors and insulators, and for that we introduced the notion of Fermi energy. From there we moved on to what we call the Fermi surface, which is again an abstract thing that happens in the reciprocal space, but is basically just a surface that separates all the occupied states of K from the unoccupied states in K, and so on and so forth. And so we have the Fermi energy, the Fermi surface, and the differences between insulators and conductors. We also discussed a little bit about what semiconductor is, which we will discuss in a little bit more detail in the coming sessions. And we will see why these materials are so important for technological reasons. In addition to that, we have discussed several details that go around these types of materials, and I hope this created now a much better intuition of the meaning of these Bloch theorem and the implications of the existence of these solutions, which are basically a plane wave which represents this electron propagating through the lattice, and the quantum solution of the Schrödinger equation with a periodic potential, which represents basically a crystal. Okay, great. Thank you very much. I think that's it for today, and I hope you will follow us in the coming sessions. So thank you very much, and see you next time. Bye.